Tonight, we are going to sit quietly at the very edge of everything at the moment before anything existed. No stars, no planets, no air to breathe, no ground to stand on, not even the darkness you might imagine, because darkness requires space, and there was none. There was no time ticking forward. There were no laws of physics waiting patiently in some cosmic waiting room. There was nothing, and from that nothing, somehow, everything came. This is perhaps the most quietly astonishing question a human mind can turn toward. How did the universe begin? Not just what happened in those first moments, though we will absolutely get there, but what does it even mean for something to come from nothing? What is nothing, really? And is the question even answerable? So settle in. Let your body grow heavier. Let the questions wash over you, not as puzzles you need to solve tonight, but as open doors leading into a very, very large and beautiful darkness. And let us begin. Before we can tell the story of the Big Bang, it is worth pausing just for a little while, here in the quiet, to think carefully about a single word. A word that seems, at first glance, so simple that it barely needs examining at all. Nothing. In the ordinary world, nothing is easy. An empty drawer is nothing. A silence between two notes in a piece of music. A blank canvas before anyone has touched it. A cup with no tea in it, which in certain households constitutes a minor emergency, but is otherwise just an empty cup. Nothing in everyday life is simply the absence of something specific. The absence of objects in a space, or of sound in a moment, or of meaning in a conversation. The space itself remains. The moment itself remains, the context holds, even when what was inside it is gone. But when physicists and cosmologists use the word nothing to describe what preceded the universe, they mean something far more radical, something that language was genuinely not built to carry. They mean not an empty space, but the absence of space itself. Not a moment of silence, but the absence of time itself. Not a blank canvas, but the absence of any surface on which a canvas could exist, any room in which it could hang, any air around it, any light to illuminate it, the absence of any laws that might govern what happens, because laws require a universe in which to operate, and there was no universe yet. It is worth saying clearly there was no darkness. Darkness is a property of space, the quality of a region of space in which very little light is present. Before the universe existed, there was no region. There was no space to be dark or bright. There was no time during which anything could be said to be happening. There was no during at all. This is the point at which human intuition, having been a reasonably good guide through most of ordinary life, quietly sits down and declines to come further. And that is completely understandable. Our minds evolved to navigate a world of objects and spaces and moments, of things that are here and not there, of events that happen before and after other events. We did not evolve to contemplate the genuine absence of all of that. It is not a failure of imagination. It is, in a strange way, a testament to how unusual the universe's origin actually is. And yet here we are. The universe exists. You exist. These words exist. Reaching you somehow across whatever distance separates the moment they were written from the moment you are receiving them. Something shifted. At some threshold, at the very boundary of comprehensibility. From nothing into something. And what is quietly astonishing, what deserves more than a moment's appreciation, is that science has actually managed to trace what happened next with extraordinary precision. Not to the very first moment, no, that part remains, perhaps permanently, beyond the reach of our current tools, but extraordinarily close to it, closer than we had any right to expect. The story of how we got from nothing to you, lying there in the dark, is one of the most remarkable stories ever assembled, and we have the whole night to tell it. It is also worth pausing before we enter the science to consider why this question matters to us the way it does. There is something almost universal in the human impulse to want to know where things come from. Children ask it instinctively, long before they have the vocabulary for cosmology. Where did I come from? Where did the world come from? Where did everything come from? It seems to be wired into the kind of minds we have, minds that are pattern-seeking, cause-seeking, always tracing the thread of any story backward to try to find where it starts. For most of human history, the answer to these questions was provided by myth and religion stories about gods or forces or primordial substances that gave rise to the world and everything in it. These stories vary enormously across cultures and centuries, but they share a common structure. Something existed before, and from that something, through some act or process, the world as we know it came to be. Science offers a different kind of answer. Not a story of intention or meaning. Science does not address those dimensions of the question, but a story of mechanism, of how rather than why. And the how, it turns out, is staggering in its detail and its strangeness and its beauty. It is a story that, once you have heard it, makes the night sky look different, makes the air you breathe feel different, knowing where its atoms have been. Makes the stars not just beautiful objects in the dark, but kin the ancestors of everything you are made of. So let us enter it carefully, with attention, and with the kind of quiet wonder that a story this large deserves. Let us begin the story at the place where science can actually plant its feet. Approximately 8 billion years ago, a number so large that it is best not to stare at it too directly, the universe as we know it came into being. This event is called the Big Bang. And almost everything that name implies is, in one way or another, a little off, which is something scientists have been politely noting for decades without managing to replace the name with anything better. The phrase has a certain stubborn staying power. It was not, in any conventional sense, a bang. A bang implies an explosion, something violent occurring at a particular point in a pre-existing space, sending matter flying outward in all directions from a center. A bomb going off, a star exploding, some catastrophic event located somewhere, surrounded by a wider emptiness into which the debris expands. The Big Bang was not like that at all. There was no surrounding emptiness. There was no location where it happened. There was no moment before it in which anything was waiting. What we call the Big Bang was not an explosion of matter into space, it was an expansion of space itself. Space, and everything in it, came into being together. Matter and energy and the very fabric of space and time all emerged simultaneously from a state of extraordinary density and heat and began expanding. Every point in space was, at that first moment, essentially touching every other point. The universe was not small the way a tennis ball is small, occupying a modest amount of space with empty space around it. It was small in the sense that space itself was compressed. The distances between things, which is to say, between all things, were essentially zero. And then those distances began to grow. Space itself stretched. And as it stretched, it carried everything within it outward, in all directions, simultaneously. The best analogy, and like all analogies, it is imperfect, but it is the best available, is the surface of a balloon being inflated. Imagine dots drawn on the surface of that balloon. As the balloon expands, every dot moves away from every other dot. No single dot is at the center. No single dot is where the expansion is coming from. From the perspective of any dot, all the others are receding. The expansion is happening everywhere at once. In the surface of the balloon itself, not into anything beyond it. Our universe is like that, except that instead of the two-dimensional surface of a balloon, we are talking about three-dimensional space. And instead of dots, we are talking about galaxies. And instead of air being blown into a rubber sphere, we are talking about the fabric of space-time itself growing, driven by forces we are only beginning to understand. This is the first place in the story where the ordinary logic of things quietly fails us, and it will not be the last. Part of what makes cosmology, the study of the universe as a whole, so genuinely fascinating is that it requires us to set aside, gently and repeatedly, the assumptions that feel most natural and follow the evidence into territory where our intuitions cannot easily go. This is the first place in the story where the ordinary logic of things quietly fails us. And it will not be the last. Part of what makes cosmology, the study of the universe as a whole, so genuinely fascinating is that it requires us to set aside, gently and repeatedly, the assumptions that feel most natural and follow the evidence into territory where our intuitions cannot easily go. That is, in a quiet way, part of what makes it worth exploring at bedtime. There is something restful about the discovery that the universe does not feel bound by what seems reasonable. Before we press on into the first seconds, it is worth a brief and gentle detour into how we know any of this at all. It is a fair question. The Big Bang happened 13.8 billion years ago. No human being was there. No instrument of any kind was there. The first stars lit up hundreds of millions of years later. The Earth formed billions of years after that. Homo sapiens appeared perhaps 250,000 years ago, and the first telescopes were built less than 500 years ago. How, from this tiny vantage point in time and space, have we managed to piece together the history of the entire universe? The answer is light. Light in physics is not merely something that helps us see. It is information, traveling at the fastest speed anything in the universe can move. When you look at the sun, you are seeing what the sun looked like 8 minutes ago. That is how long its light took to travel to your eyes. When you look at the nearest star beyond the sun, you are seeing it as it was 4 years ago. When you look at the Andromeda galaxy on a clear night, a faint smear of light visible to the naked eye, you are seeing it as it was 2.5 million years ago. The further away something is, the further back in time we are seeing it. And because the universe is so vast, we can look back enormous distances in time simply by looking at things that are far enough away. The most distant galaxies we have observed with instruments like the James Webb Space Telescope are so far away that their light has been traveling for more than 13 billion years. We are seeing them as they were when the universe was less than 1 billion years old. This is not an approximation. It is a direct consequence of the finite speed of light, which is one of the most precisely measured quantities in all of science, approximately 299,792 kilometers per second. Light speed is the same everywhere in the universe, for every observer, regardless of how fast they are moving. This constancy, one of the foundational results of Einstein's special theory of relativity, is what makes the universe's history readable in its light. And then there is the cosmic microwave background, which we will encounter shortly, and the abundances of elements, and the way galaxies cluster and filament across space. Each of these is a different kind of record, a different page in the cosmic archive, readable with instruments of sufficient sensitivity. We have been very lucky as a species to develop both the curiosity and the mathematical tools needed to read these pages. And we are still reading. Now, the very first moments. We cannot directly observe the universe in its absolute first instant. The mathematics we use to describe the physics of space and time, Einstein's general theory of relativity, breaks down completely when we try to apply it to the conditions that would have existed at the very beginning. Temperature and density become, in the equations, infinite, and infinite, in this context, is not a description of something very large. It is a signal that the theory has reached its own boundary, that something in our understanding is missing. Something important remains to be discovered. This breakdown is not a failure of the theory in any other respect. General relativity is one of the most precisely tested and confirmed theories in all of science. It correctly predicts the behavior of gravity in nearly every situation we can test, but at the singularity, the name given to that first moment of infinite density, it stops. It reaches a wall. And what lies on the other side of that wall is, for now, one of the great open questions in physics. But here is the remarkable thing. We do not need to reach all the way back to that first instant to tell a fascinating and scientifically grounded story. We can begin a tiny, tiny fraction of a second later. A fraction of a second so small that no human vocabulary of smallness really does it justice, something on the order of 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second after the beginning. And at that point, even that young, even that close to the very edge of everything, we can say something scientifically meaningful about what the universe was like. And what it was like was this: extraordinarily hot, extraordinarily dense, and extraordinarily strange by the standards of anything we encounter in everyday life. The temperatures in those first moments were so extreme, we are talking about numbers in the trillions of degrees. And beyond that, the very concept of ordinary matter had no meaning. The things we think of as the fundamental building blocks of the world, protons, neutrons, the atoms they form, could not exist at those temperatures. The conditions were so energetic that matter and energy blurred together, interchanging freely. Einstein's famous equation, the one about energy equaling mass multiplied by the speed of light squared, was not a curiosity in those first moments. It was a description of reality in real time. Energy was becoming matter, and matter was dissolving back into energy, constantly in all directions at once. The universe in those first moments was a searing, churning, almost indescribably energetic soup. There were quarks, the tiny particles that in cooler and quieter conditions clumped together to form protons and neutrons. There were electrons zipping through the plasma at nearly the speed of light. There were photons, particles of light in enormous abundance, colliding with everything, unable to travel more than the tiniest distance before hitting something else. There were neutrinos, ghostly particles that barely interact with anything, but were present in staggering numbers. There were the particles that carry the fundamental forces, the gluons that hold quarks together, the bosons associated with the weak nuclear force. Everything was present. Everything was interacting. Everything was in furious, continuous, spectacular motion. If you had been able to stand there, which you could not, for reasons that go rather beyond the obvious practical difficulties, you would not have seen anything. Not because it was dark. There was an almost unimaginable flood of light. But the light had nowhere to go. The plasma was so dense that a photon could travel no distance at all before being absorbed or scattered by the particles surrounding it. The universe was opaque, brilliant, searing, and completely opaque. And then, very slowly by cosmic standards, the universe began to cool. There is something else worth mentioning about those first extraordinary moments, something that gives the story an additional layer of quiet depth. Today, nature operates through 4 fundamental forces. Gravity, which governs the large-scale structure of the universe, the orbits of planets, the collapse of stars, the clustering of galaxies. Electromagnetism, which governs the interaction of charged particles, the behavior of light, the chemistry of atoms and molecules. The strong nuclear force, which holds the nuclei of atoms together against the electromagnetic repulsion between their protons. And the weak nuclear force, which governs certain kinds of radioactive decay and plays a critical role in how stars produce energy. These 4 forces appear, today, to be quite distinct. They operate over different ranges with different strengths through different carrier particles. A physicist working with electromagnetism and a physicist working with gravity are in many respects working with very different tools. But there are strong theoretical reasons and some observational hints that in the extreme heat of the earliest universe, these forces were not distinct at all. They were unified. At sufficiently high temperatures and energies, the differences between the forces dissolve, and what we perceive as 4 separate phenomena merge into far fewer, perhaps into one. The moment at which even gravity unified with the other forces is called the Planck epoch, and it corresponds to temperatures and energy scales so extreme that our current physics has nothing to say about it. This is precisely where the mathematics breaks down, where the theory produces infinities and loses its ability to make predictions. It is the edge of the map, the place beyond which our tools do not work. And it is one of the deepest motivations for research in theoretical physics today to develop a framework that can handle both quantum mechanics and gravity simultaneously, because that framework would allow us to describe what was happening in those first unimaginably brief moments. Various candidates exist. String theory is perhaps the most widely discussed, though it remains unproven. Loop quantum gravity is another. There are others still, each making different predictions about the Planck scale structure of space and time. None of them has yet been confirmed by experiment. None may be for some time, or perhaps ever, given the enormous energies involved. But as the universe cooled from those extreme early conditions, the forces separated from one another, one by one, in a process physicists call symmetry breaking. Gravity separated first. Then the strong nuclear force. Then the electromagnetic and weak forces separated from each other. In an event that we believe occurred at a temperature of about 1 quadrillion degrees of temperature that our most powerful particle accelerators have very recently and very briefly approached. With each separation, each new distinction between forces, the universe became more structured, more varied, more capable of producing complex things. It is as though the universe was revealing itself in stages, each phase of cooling uncovering new possibilities that the heat of earlier moments had kept compressed and hidden. The rich variety of particles and forces and atoms and molecules and stars and galaxies and living things that we see today was, in the first moment, all bundled together in a single undifferentiated state of extraordinary simplicity and heat. We are, in a sense, the product of an extraordinarily long cooling process. Cooling, in the universe's early history, is not simply a matter of temperature dropping. It is a story of structure emerging. As the universe expanded and the space between its particles grew, the frantic, energetic collisions that had been preventing anything from holding together became rarer. The universe, little by little, became a slightly calmer place. And as it calmed, things that had been impossible in the heat started to become possible. The first major threshold came at around 1/10,000th of a second after the Big Bang. By that point, the universe had cooled enough, if we can use that word for temperatures still well into the trillions of degrees, for quarks to stop flying freely and begin binding together. 3 quarks, pulled toward each other by the strong nuclear force, formed protons. 3 quarks in a slightly different configuration formed neutrons. These tiny, dense particles, far smaller than atoms, stabilized in those first fractions of a second. They are still with us today. The proton at the center of every hydrogen atom in your body was formed in that brief window of time, in conditions so extreme that no laboratory on Earth has ever come close to recreating them. For a brief period there were also antiparticles, an antiproton for every proton, an antineutron for every neutron. Matter and antimatter, produced in almost exactly equal numbers by the energetic conditions of the early universe. And when matter and antimatter meet, they annihilate each other, vanishing in a flash of pure energy. Which raises a question that is worth pausing on, because it is one of the most important questions in cosmology. We exist. Which means matter won. Which means there was a slight excess of matter over antimatter, roughly 1 extra particle of matter for every billion matter-antimatter pairs. Why? What caused this tiny asymmetry? The honest answer is that we do not fully know. There are theories, some of them quite mathematically elegant, but none of them has been confirmed to the degree that would settle the question. What we know is that without that slight imbalance, without that fractional excess of matter over antimatter, every particle produced in the Big Bang would have been annihilated. the universe would have consisted of nothing but light. No stars, no galaxies, no planets, no curious minds wondering how it all began. That quiet, fractional asymmetry is, in a very real sense, the reason you exist. About 3 minutes after the Big Bang, and it is worth pausing every time we say something like 3 minutes after the Big Bang, because that sentence contains multitudes the universe had cooled enough for protons and neutrons to begin sticking to each other. Not into full atoms, electrons were still far too energetic, and the temperatures far too high for that. But the nuclei, the dense central cores of atoms, began to form. This process is called Big Bang nucleosynthesis, which is a phrase that sounds far more complicated than what it is describing. It simply means the formation of atomic nuclei in the first minutes after the Big Bang. And what it produced was predominantly hydrogen. Hydrogen is the simplest element, a single proton, sitting on its own, needing nothing else to be itself. In the very hot, very dense early universe, most protons never acquired a neutron companion. They became, and remained, hydrogen nuclei. Some protons and neutrons did combine. 2 protons and 2 neutrons, bound tightly together by the strong nuclear force, form the nucleus of helium. And in the early universe, roughly 25% of all the normal matter that existed became helium-4 in this way. About 1 in 12 protons ended up in a helium nucleus, while the rest remained as lone hydrogen nuclei. There were also tiny amounts of other light elements, trace quantities of helium-3, deuterium, which is a form of hydrogen with 1 neutron added, and the lightest form of lithium. These were produced in very small quantities, and they are still there today, embedded in the oldest and least altered clouds of gas in the universe, providing a kind of chemical fingerprint of what the Big Bang produced. When astronomers measure the abundance of these elements in ancient gas clouds and compare them to the predictions of Big Bang nucleosynthesis, the agreement is remarkably close. It is one of the strongest pieces of evidence we have that our understanding of the early universe is correct. But beyond those light elements, hydrogen, helium, a whisper of lithium, the early universe had nothing else. No carbon, no oxygen, no iron, no calcium, no silicon, no nitrogen. Every element heavier than lithium that exists anywhere in the universe today was made later, inside stars, and we will come to that in due course. This is worth sitting with for a moment because it is genuinely extraordinary. Every periodic table you have ever seen, that elegant grid of elements, from hydrogen at the top, left through uranium and beyond, represents over 100 distinct kinds of atoms. Of those, the Big Bang produced meaningful quantities of exactly 3: hydrogen, helium, and a small trace of lithium. The other 100+ elements came later, built one by one in the nuclear furnaces of stars. The periodic table, in that sense, is not just a chart of chemistry. It is a map of cosmic history. The heavier an element is, the later in the story it was made, and the more dramatic the stellar processes required to make it. Iron, for instance, sits roughly in the middle of the periodic table. It is the endpoint of nuclear fusion in the core of a massive star, the element at which fusion becomes energetically unfavorable, and which, when it accumulates in sufficient quantities, triggers the catastrophic collapse that ends the star's life. The gold in a piece of jewelry, or the uranium in a nuclear reactor, is heavier than iron and was not made by ordinary stellar fusion at all. It required conditions found only in the collision of two neutron stars, or in the extreme shock waves of a supernova's final moments. Every gold atom that has ever existed was made in an event of almost incomprehensible violence, in a universe far younger than it is today. The early universe, with its three elements, was not yet capable of any of this. It was, in the grand scheme of chemistry, extraordinarily simple. But it held within its hydrogen and helium all the potential that would, over billions of years, unfold into everything that came after. For now, the universe settled into what would be a very long, very hot, very opaque period. Hundreds of thousands of years of a plasma of nuclei and electrons and photons, all tangled together in an expanding, slowly cooling sea. 380,000 years after the Big Bang. Let us sit with that number for a moment. 380,000 years. This is longer than the entire span of modern human prehistory, longer than the entire time our species has existed on Earth. And in the life of the universe, it is barely an opening breath. For all of those thousands of years, the universe was opaque. Light could not travel freely. Every photon that was emitted was almost immediately scattered, bounced off an electron, redirected, scattered again. The universe was a kind of luminous fog, filled with energy, filled with light, but impossible to see through. It was bright, in a sense, but not transparent. A photon produced at one end of the observable universe could not possibly reach the other end. It would travel a tiny distance and then careen into a free electron and be sent in a new direction. And then, at around 380,000 years after the Big Bang, something happened that changed everything. The universe had cooled to about 3,000 degrees, still extraordinarily hot by any earthly standard, but cool enough for something that had never before been possible. Electrons, which had until this point been free-ranging and energetic, began to settle. They slowed enough that the electric attraction between them and the positively charged atomic nuclei around them could take hold. They dropped into stable orbits. They combined with nuclei to form the first complete neutral atoms. In physics, this moment is called recombination. The name is slightly misleading. As we touched on earlier, it implies a reunion of things that had been together before, when in fact electrons and nuclei had never been combined prior to this moment. They had always been separate. This was their first meeting, not a reunion. History has decided not to revisit this naming decision, and we move on. When neutral atoms formed, the free electrons that had been scattering all the photons disappeared. They were captured. And with the scatterers gone, light was suddenly, for the first time in cosmic history, free to travel. Photons that had previously been trapped in the thick plasma could now move in straight lines across the universe, covering enormous distances without interruption. The universe became transparent in what was, cosmically speaking, a remarkably short time. The fog lifted, and as it did, a flash of light was released aglow, filling all of space. The thermal radiation of a universe at 3,000 degrees suddenly freed to travel. That light is still traveling today. It has been moving through space for nearly 13.8 billion years. As the universe expanded around it, the wavelength of that ancient light was shifted from the warm glow of visible light into the much longer wavelengths of microwave radiation. And so today it fills the entire sky in every direction as a faint and extraordinarily uniform bath of microwave energy. It has a temperature of just under 2.7 degrees above absolute zero. It is called the cosmic microwave background radiation, and it is, without any exaggeration, one of the most important things ever detected. When astronomers point sensitive instruments at the sky and measure this ancient glow, they are not looking at something nearby. They are looking at the surface of last scattering the layer of the early universe from which those photons were released, 380. 0 years after the Big Bang. They are, in the most literal sense available, looking back almost to the beginning. They are seeing the oldest light in the universe. But it is not the existence of this glow that is most remarkable. It is what is within it. The cosmic microwave background is not perfectly uniform. It is almost perfectly uniform. The variations in temperature across the sky are tiny, on the order of 1 part in 100,000. But they are there. And they are not random noise. They are a structured pattern, imprinted on the universe by the physics of that first 380,000 years, the slight variations in density that existed in the early universe, the acoustic oscillations of that primordial plasma, the gravitational influences of whatever seeds of structure were present from the very beginning. These patterns are, in effect, a photograph of the universe at 380 years old. And embedded within those patterns are the seeds of everything that came afterward, every galaxy, every cluster of galaxies, every vast structure that would take billions of years to grow. When we look at the cosmic microwave background, we are looking at the blueprints of the cosmos written in light that has been traveling since before a single star existed. Astronomers have mapped this ancient glow in extraordinary detail, using satellites like COBE, MAP, and the Planck satellite. The precision of these measurements and the extraordinary agreement between what is observed and what the theory of the Big Bang predicts is one of the things that gives cosmologists genuine confidence that they are on the right track. After recombination, the universe entered a period that is sometimes called the Cosmic Dark Ages. It is a fitting name. The light that had been freed at recombination was real, it was there, filling space. But there were no stars yet, no galaxies, no compact sources of light of any kind. The photons released at recombination had already spread out and stretched into longer and longer wavelengths, and the universe contained nothing but vast, thin, slowly expanding clouds of hydrogen and helium gas drifting in an expanding darkness. Try to picture it, or rather, try to let the picture form without forcing it. A universe that extends in all directions without limit. A cosmos filled with gas, not the thick, warm air of a room, but gas of extraordinary thinness, billions of times less dense than the best vacuum that can be created in any laboratory on Earth. And through this thin gas, no light, no warmth, no radiation of any significance, just the slow, steady expansion of space, carrying everything within it apart from everything else. The gas growing thinner, the universe growing dark, and, for what would turn out to be somewhere between 150 million and 800 million years, nothing else. This is a vast span of time. If the entire history of the universe were compressed into a single year, the cosmic dark ages would occupy roughly the first 1 to 2 weeks of January. During those weeks, not a single star would shine. Not a single photon from a luminous object would cross the void. The universe would be quiet in a way that has no equivalent anywhere in the world we know. And yet, within this silence, something was happening that would change everything. Gravity was working. Gravity is, in a way, the most patient force in nature. It does not require extreme conditions to operate. It does not need high temperatures or high densities. It works at every scale, across every distance, and it never stops. And in the dark universe of those early hundreds of millions of years, gravity was slowly, steadily doing what it always does, pulling things toward each other. The gas was not perfectly uniform. There were slight variations in density regions where the gas was fractionally denser than average and regions where it was fractionally thinner. These variations were tiny, but they were there, baked into the structure of the universe from the patterns we saw in the cosmic microwave background. And wherever the gas was slightly denser, gravity was very slightly stronger. So the slightly denser regions pulled in gas from their surroundings. And as they grew denser, they pulled harder. And as they pulled harder, more gas flowed in. And the process built on itself, slowly but continuously, across millions of years. There is something deeply calming about this image, if you let it settle. The universe, in the dark, quietly building. No drama. No catastrophe. Just the soft, constant accumulation of gas drawn toward gas, over millions of years in silence. Nothing to see, nothing to hear. Just the invisible architecture of the future, assembling itself in the dark. And here is where dark matter plays a role that is worth understanding. Because it is not a minor supporting character in this story. It is, in many ways, the scaffolding on which everything else was built. Dark matter does not interact with light. It does not emit it, absorb it, or reflect it. If you shone a flashlight at a cloud of dark matter, the beam would pass straight through with no effect whatsoever. This is why dark matter is dark, in the physical sense, not because it is in shadow, but because it is genuinely invisible to electromagnetic radiation of any wavelength. But dark matter does interact gravitationally. It has mass, and mass curves space, and curved space exerts a gravitational pull. And because dark matter was present in enormous quantities in the early universe, making up roughly 5 times as much mass as ordinary matter, its gravitational influence was enormous. It was dark matter, clustering under its own gravity in the Dark Ages, that first built the large-scale structure of the universe. The vast filaments and sheets and clusters of matter that today trace the 3-dimensional architecture of the cosmos, what is sometimes called the cosmic web, were seeded by the gravitational clustering of dark matter in those first hundreds of millions of years. Ordinary matter, hydrogen and helium gas, simply fell into the gravitational wells that dark matter had already prepared. The dark matter formed the structure, the gas followed. And where the gas was densest, in the deep center of those dark matter concentrations, the temperature and pressure climbed high enough for fusion to ignite. The thin wisps of gas in the denser regions began to gather into larger clouds. Those clouds grew. They cooled as they did, releasing heat as they compressed, but also stretching and thinning in the outer parts where gas was being drawn inward. And inside the densest, most collapsed parts of these gathering clouds, temperatures began to rise again. Pressure built. Density built. The gas at the centers of these forming clouds grew hotter and hotter, compressed under the weight of all the gas above it, pressing in from all sides. And eventually, in the cores of the densest of these clouds, something happened that had never happened before in the history of the universe. The temperature climbed high enough, around 10 million degrees, for hydrogen nuclei to begin fusing. Nuclear fusion. The process by which the cores of light nuclei are forced close enough together that they can merge into heavier nuclei, releasing an enormous amount of energy in the process. The first star lit up. This moment, cosmic dawn, as it is sometimes called, is one of the most significant thresholds in the entire history of the universe. Hundreds of millions of years of darkness, and then, in some cloud of collapsing gas in some part of the early cosmos, a new light flickered into being. A star. And then another. And then more, as other clouds crossed the same threshold, as the same process of gravitational collapse and heating and ignition played out across the universe. Within a few 100 million years of the Dark Ages beginning to end, the cosmos was lit with the light of those first stars. What were these first stars like? They were not like the stars we see when we look at the night sky today. They were almost certainly far more massive, some of them possibly hundreds of times the mass of our own sun, perhaps even approaching 1,000 times as massive. They were made of essentially pure hydrogen and helium, because those were the only elements that existed in the universe at the time. And their extreme mass meant that the pressure and temperature at their cores were extraordinarily far more extreme than in a smaller, gentler star like our sun. They burned ferociously. They consumed their hydrogen fuel at a rate so rapid that their lifespans were measured not in billions of years, as the sun's will be, but in millions. Some of the most massive may have burned for only a few million years before exhausting their fuel entirely. And when they did exhaust their fuel, they died in the most dramatic way available to physics. A star lives in a kind of balance. The gravity of all its mass pulls inward, trying to collapse the star. The energy produced by nuclear fusion in the core pushes outward, a constant pressure that keeps the star from collapsing. As long as fusion is producing energy, the balance holds. But when the fuel is exhausted, the outward pressure fails. And then gravity wins, very suddenly. The core collapses. In the most massive stars, this collapse happens in a fraction of a second, a catastrophic infall that is so rapid and so violent that it triggers a rebound, an explosive shock wave that blasts the outer layers of the star outward in all directions. This is a supernova. One of the most energetic events in the universe, releasing in moments more energy than our sun will produce over 10 billion years. But what came out of that explosion was not nothing. What came out was new. Because inside that dying star, in the extreme temperatures of its final stages, something remarkable had been happening. The hydrogen and helium in the core had been fusing into heavier elements. Helium fused into carbon and oxygen. Carbon fused into neon and magnesium. Heavier and heavier elements were produced, layer by layer, in the final stages of the star's life, as it burned through its reserves and tried to find new fuels. Iron formed last. And iron is where fusion stops. It takes more energy to fuse iron than the process releases, so when the core of a massive star becomes iron, fusion ceases and collapse is inevitable. And in the supernova that follows, the energies are so extreme that elements heavier than iron can form briefly in the shock wave. Gold, silver, uranium. These are elements that can only be forged in the extraordinary conditions of a dying star's final moments, or in the merger of two neutron stars, the collapsed remnants of stellar cores, which are among the most violent and energetic events in the universe. All of this material, this library of newly created elements, the first heavy atoms in the history of the universe, is blasted outward by the supernova explosion. It spreads through the surrounding space. It mingles with the remaining hydrogen and helium gas. It enriches the clouds of gas from which the next generation of stars will form. Carbon, oxygen, nitrogen, iron, the elements without which life as we understand it cannot exist. They were not present in the universe before those first stars. They were made inside them, in the nuclear furnaces of their cores over millions of years. And they were released into the universe by the deaths of those stars, scattered across the cosmos in expanding shells of supernova debris. When we say that we are made of stardust, we are not speaking poetically. We are speaking with chemical precision. Every carbon atom in every molecule of every cell of your body was produced by nuclear fusion in the interior of a star. The oxygen in your lungs was forged in a stellar core. The calcium in your bones, the iron in your blood, the nitrogen in your DNA, these were all produced inside stars that lived and died long before our solar system came into being. They entered the cosmic gas supply. And much later they found their way into you. The universe made you piece by piece over billions of years. It just did not know it was doing so. The first stars died and scattered their newly made elements into the surrounding gas, and from that enriched gas, a second generation of stars formed. And a third. And with each generation, the gas of the universe grew richer in heavy elements, the raw material of planets and chemistry, and, eventually, biology. Meanwhile, at larger scales, something equally important was unfolding. Gravity was not just gathering gas into individual stars. It was gathering stars into much larger structures. The same process of collapse and concentration that had created the first stars was also, at scales 100,000 times larger, assembling galaxies. A galaxy is, at its simplest, a gravitationally bound collection of stars, gas, dust, and, as we will explore shortly, something invisible called dark matter. Our own galaxy, the Milky Way, contains somewhere in the region of 200 to 400 billion stars. It is roughly 100,000 light-years across, which is to say that light travelling at the fastest speed anything in the universe can travel would take 100,000 years to cross it from one edge to the other. The Milky Way is, by most measures, an average galaxy, not the smallest, not the largest, somewhere in the wide and varied middle. It began to form very early in cosmic history, perhaps 12 or 13 billion years ago, within the first billion years or so after the Big Bang. It grew, not all at once, but through a long process of accretion and merging. Smaller galaxies, called dwarf galaxies, fell into its gravitational embrace and were absorbed. Streams of gas and newly formed stars flowed in from the surrounding environment. Over billions of years, the loose, irregular structure of the young Milky Way settled slowly into the familiar shape we see today, a disk of stars with spiral arms wrapped around a dense central bulge with a supermassive black hole at its very center. Every galaxy in the universe has, at its center, a supermassive black hole. These are objects of almost incomprehensible mass. The one at the center of the Milky Way, known as Sagittarius A, contains the mass of roughly 4 million suns, compressed into a region smaller than the distance from the Sun to Mercury. The black holes at the centers of larger galaxies can be billions of times the mass of the Sun. In the early universe, these central black holes were often violently active. Gas was flowing into them in enormous quantities, and as it did, it heated up just as gas heats when compressed and released tremendous amounts of energy as radiation. These blazing, intensely luminous objects are called quasars. A quasar at the center of a young galaxy can outshine the entire galaxy by a factor of hundreds, radiating more light than 100 billion suns combined. They are among the brightest objects in the universe, and they are detectable across billions of light years, which is why, when we look at the very early universe, we can see them. The universe in those early billions of years was a busy, turbulent, energetic place. Galaxies forming, colliding, merging, quasars blazing at their centers, stars being born and dying in rapid succession. The cosmos was assembling itself, with gravity as the tireless architect. And slowly, over billions of years, the pace of activity eased. Gas was consumed by stars or ejected from galaxies. Quasars dimmed as their black holes ran low on fuel. The rate of star formation, which had peaked somewhere around 10 billion years ago, began to decline. The universe grew gradually quieter, gradually older, gradually more spread out. And so we arrive about 4.6 billion years ago at a particular moment in the Milky Way. A cloud of gas and dust, parked in one of the galaxy's spiral arms, begins to collapse. It is not a remarkable cloud. It is not especially large or especially dense or especially unusual in any way. It is the kind of cloud that forms and collapses and gives rise to stars millions of times across the history of any galaxy. But this one is ours. What triggered its collapse is not entirely certain. One popular idea is that a nearby supernova sent a shockwave through the cloud, compressing it enough to begin the process of gravitational collapse. If so, then the death of an ancient star that had been living out its final moments long before our sun existed was, in some indirect sense, the trigger for the birth of our solar system. The cosmos, as it often does, recycled something old into something new. As the cloud collapsed, it began to spin a slow rotation, the result of tiny irregularities in the original gas cloud being amplified as the cloud compressed, the same way a figure skater spins faster as they pull their arms inward. Conservation of angular momentum, as it is called, is an extraordinarily reliable principle. It shaped the cloud of gas that became our solar system, just as it shapes the motion of storms and the spiral arms of galaxies and the orbits of moons. At the center of the collapsing cloud, temperatures rose. The density climbed. And roughly 4.6 billion years ago, a star ignited in the core of that cloud. Our sun. A somewhat unspectacular, Middle-aged star of average mass and average brightness, destined to burn steadily for 10 billion years, total of which it has now consumed just under half. The remaining gas and dust, not pulled directly into the forming star, was flung outward by the spin and settled into a flat, rotating disk around the young sun. And within that disk, the process of accumulation began. Dust grains collided and stuck together. Larger and larger clumps formed. Over millions of years, these clumps, called planetesimals, grew through continued collisions into larger bodies. The larger bodies had more gravity, which allowed them to pull in even more material. And through this gradual, patient process of accretion, the 8 planets of our solar system assembled themselves from the debris of ancient stars. One of them, the 3rd planet from the Sun, a rocky world at just the right distance from its star to maintain liquid water on its surface, would turn out to be remarkably interesting. The Earth formed about 4.5 billion years ago. For the first several 100 million years of its existence, it was a violent place bombarded by asteroids and comets, geologically active to a degree that would make anything alive today profoundly uncomfortable, lacking the breathable atmosphere that later life would both depend on and create. The Moon formed early in Earth's history, the result of a collision between the young Earth and another planetary body roughly the size of Mars. The debris from that collision was flung into orbit and slowly coalesced into the Moon we see today. And then, somewhere in the chaos of those early hundreds of millions of years, something remarkable happened. In the warm, chemically rich waters of the early Earth, perhaps in tidal pools, perhaps near volcanic vents on the seafloor, perhaps in some other setting we have not yet identified, the right combination of molecules came together. Chemistry crossed a threshold. Self-replicating molecules appeared. Life began. Within roughly 1 billion years of Earth's formation, life was already present. Single-celled organisms, simple and small, but alive, consuming energy, reproducing, adapting over generations. Life proved, once it had started, to be tenacious in a way that few things in nature can match. It spread, it diversified, it transformed the planet around it, most dramatically in an event called the Great Oxidation Event. About 4 billion years ago, when photosynthetic bacteria began releasing oxygen into the atmosphere in quantities large enough to fundamentally alter its chemistry. And then, over the billions of years that followed, life grew more complex. Cells with nuclei appeared, multicellular organisms appeared, the oceans filled with creatures of bewildering variety. Life climbed onto land, forests grew, insects flew. Reptiles dominated the land for hundreds of millions of years. A mass extinction cleared the stage. Mammals diversified. Primates evolved, and eventually, perhaps 250,000 years ago, a particular species of primate appeared in Africa. A species with an unusually large brain relative to its body size, and an unusual tendency to be curious about things that had no immediate bearing on its survival. Those creatures looked up at the sky, and they began to wonder. It is worth pausing here for a moment, because this point in the story, the arrival of minds capable of contemplating the universe, is genuinely significant, in a way that goes beyond the merely remarkable. Consider what it means. For the first 13.8 billion years of its existence, The universe was a place without awareness. Not just without human awareness, without any awareness at all as far as we know. Stars burned and died and scattered their elements across space entirely without witness. Galaxies assembled themselves in the dark over billions of years with no one to observe them. Black holes swallowed matter and bent the fabric of space-time, and there was no consciousness anywhere to register these events. The universe, for most of its history, was going about its extraordinary business in total silence, without observation, without meaning attributed to it by any mind. And then, on one small world, in one quiet corner of one average galaxy, a series of chemical accidents led to self-replicating molecules. And those molecules, over billions of years of evolution, produced creatures capable of asking questions about their own existence, creatures capable of building instruments of sufficient sensitivity to detect the faint glow of the universe's infancy, creatures capable of constructing the mathematics needed to describe what happened before any star existed. In that sense, we are how the universe knows itself. We are not separate from the cosmos, looking in from some external position. We grew from it, assembled by the same processes that assembled everything else, and we carry within us the history of everything that came before. The curiosity you feel, right now, reaching gently toward these ideas that curiosity is, in the most literal sense, the universe reaching toward understanding of itself. That thought is worth letting rest quietly in the mind for a moment. It is, in the most gently understated way possible, quite a journey to have taken. We have now traced the story from the very first fractions of a second all the way to this moment to you, here in the quiet, drifting towards sleep. But throughout this telling, we have been carefully circling around the deepest question of all, the one that lives at the very center of everything we have described. The one that the story of the Big Bang and of everything that followed does not by itself answer. Where did the Big Bang come from? What was the state of things before it? Was there a before? Is that even a meaningful question? What was the nothing that became something? And can science say anything useful about it, or is this the place where the lights simply go out and human knowledge stops? These are questions that deserve honest, careful attention. Because they are real questions, and because the honest answer, the most truthful thing that can be said, is that we do not know. Not yet. Perhaps not ever, in the full sense. But science has not simply retreated from this boundary. It has walked right up to it, and in doing so has produced some of the most fascinating and thought-provoking ideas in all of intellectual history. There is also something genuinely peaceful about sitting at this boundary, if you allow it. The universe's origin is not a failure of human knowledge. It is a horizon, the kind of limit that makes it clear how far we have come and how much further there is yet to go. Every generation of scientists and thinkers that has turned toward these questions has left the map slightly more detailed than they found it. And every honest acknowledgement of what remains unknown is in its own way a mark of intellectual integrity. Let us spend some time with those ideas. The most widely discussed explanation for what happened in the very earliest moments of the universe is a process known as cosmic inflation. The idea of inflation was developed primarily in the early 1980s by a physicist named Alan Guth, working at the time at the Stanford Linear Accelerator Center with important contributions from Andre Lindy, Paul Steinhardt, and others. The central proposal of inflation is this: in an extraordinarily brief period of time immediately following the Big Bang, so brief that the number used to describe it has 36 zeros after the decimal point before it reaches any non-zero digit, the universe underwent a phase of expansion so rapid that fast is not even remotely an adequate word for it. In that fraction of a moment, the universe expanded by a factor of at least 10 to the power of 26. To write this as a number, you would write the digit 1 and then follow it with 26 zeros. If you tried to convey the size of this factor using an analogy, say, by comparing it to the number of atoms in the observable universe, or to the number of seconds since the Big Bang, you would find that even these already staggering numbers do not come close to capturing it. The expansion of the universe during inflation was not merely fast. It was, in any human vocabulary, incomprehensibly fast. What drove this expansion? In most models of inflation, the driving force was a quantum field, a kind of energy distributed through space that was in a particular high-energy state in those first moments. Fields of this kind, in quantum physics, can cause space to expand rapidly, and the inflaton field, as it is called, appears to have done exactly that. As the universe inflated, this field slowly decayed toward a lower energy state. And when it reached that lower state, when inflation ended, the energy it had been carrying was converted into a burst of heat and particle production. This event, called reheating, essentially refilled the universe with the hot, dense plasma of particles that we described earlier as the starting conditions for the conventional Big Bang story. Inflation is not merely a speculative add-on to cosmology. It makes specific, testable predictions, and many of them have been confirmed. It predicts that the universe should appear geometrically flat, and indeed, measurements of the cosmic microwave background show the universe to be flat to extraordinary precision. It predicts that the temperature of the cosmic microwave background should be nearly uniform across the whole sky, because regions that appear too far apart to have ever communicated were, before inflation, in very close contact, and indeed, the CMB is uniform to 1 part in 100,000. It predicts a specific pattern of fluctuations in the CMB, and the pattern we observe matches those predictions well. Inflation is not proven. It remains, in the careful sense of the word, a theory, meaning a powerful, evidence-supported explanatory framework, not a casual guess. There are different versions of inflation, and some details are still debated. But it represents our best current account of what happened in the universe's earliest moments. And yet inflation does not answer the deepest question. It tells us what the universe did in its first instance. It does not tell us where the inflaton field came from. It does not tell us what caused the initial state. It pushes the mystery back one step further, which is progress genuinely, but it is not an ending. One of the most fascinating responses to this deeper question comes from the physicist Stephen Hawking, working with the mathematician James Hartle. It is called the Hartle-Hawking no-boundary proposal, and it is one of those ideas that is best encountered in a state of comfortable relaxation, because it requires letting go of some fairly fundamental assumptions about what questions are valid. The proposal begins with an observation about the nature of time. Time, as we experience it, flows in one direction. It has a quality of progression. Events happen in sequence. The past is fixed. The future is open. And it seems natural to ask what came before any given event, tracing the chain of causes back through time. But Hartle and Hawking pointed out that time in physics is not separate from the universe. Time is a dimension of space-time, and space-time is what the universe is made of. Before the universe existed, there was no time. And asking what came before the universe is, in this view, a question that dissolves on examination. The way asking what is south of the South Pole dissolves on examination. The South Pole is the southernmost point on Earth. There is no south of it. The concept simply stops making sense at that point. Similarly, Hartle and Hawking proposed that the concept of before the Big Bang may simply not be a coherent concept. Not because the question is unanswerable, but because the question itself does not correctly apply to reality. In their mathematical framework, which uses a technique called imaginary time, a genuine mathematical concept, not a poetic one, the universe has no boundary in time. It does not begin at a sharp edge. It curves smoothly in a way that makes the concept of a starting moment unnecessary, much as the surface of a sphere has no edge. The universe simply is, without ever having begun, in a way that requires an external cause. Hawking was fond of pointing out that this framework implies the universe is genuinely self-contained. It would require no external force, no creator, no cause beyond itself. Whether this satisfies the philosophical curiosity about why the universe exists, rather than nothing that is a question each person must sit with for themselves. There is another deeply interesting idea about cosmic origins that comes not from general relativity, but from quantum mechanics, the branch of physics that describes the behavior of things at the smallest scales. One of the most counterintuitive features of quantum mechanics is a phenomenon called quantum tunneling. In classical physics, the kind of physics that describes the everyday world of balls and cars and falling objects, an object that does not have enough energy to cross a barrier simply does not cross it. A ball rolled at a hill with too little speed will not make it over the top. It rolls back. But at the quantum scale, particles do not follow this rule. There is a genuine, measurable, reproducible phenomenon in which particles cross barriers they should not have enough energy to cross. Not by going around the barrier, not by being given extra energy, by genuinely passing through it in a way that defies classical intuition but follows rigorously from the mathematics of quantum mechanics. This is called tunneling, and it is not a metaphor or an approximation. It is a real thing that happens in the world, and it underlies the operation of many technologies, including certain kinds of microscopes and transistors. The physicist Alexander Vilenkin, among others, has proposed that the universe itself may have arisen through a process analogous to quantum tunneling. In this picture, the universe tunneled into existence from a state of literal nothingness, not a vacuum. Not empty space, but truly nothing, driven by the probabilistic nature of quantum mechanics. Just as a particle can spontaneously appear on the other side of a barrier it should not be able to cross, a universe can spontaneously appear from the absence of any prior state. Because quantum mechanics does not require things to have classical causes in the way we intuitively expect. Vilenkin has described this with a phrase worth turning over quietly in the mind: the universe is the ultimate free lunch. By which he means that if quantum mechanics applies even to the question of the universe's own existence, then the universe may have cost nothing to create, because quantum tunneling requires no input of energy or matter. It is a fluctuation from nothing arising not in defiance of the laws of physics, but as a consequence of them. This idea implies something philosophically significant. In a quantum mechanical universe, nothing is not a stable state. True nothingness is, in this view, inherently unstable. Left alone long enough, or left alone even for the most infinitesimal duration, nothingness will, with some probability, give rise to something. Not because something caused it to, but because the laws of quantum probability make it inevitable. Nothingness, in this picture, contains within it the seeds of its own dissolution. Whether this is correct, we genuinely do not know. It is a speculative framework, beautiful in its mathematical coherence, but not yet testable in any direct sense. It sits at the very boundary of what physics can currently address. But it is the kind of idea that is worth holding, gently, as you drift towards sleep. Then there is the possibility one that arises quite naturally from inflationary cosmology, that our universe is not the only one. Inflation, as we described it, is driven by a quantum field in a high-energy state. But quantum fields are subject to quantum fluctuations, small, random variations in their energy that are a fundamental feature of quantum mechanics rather than a defect in our measurements. In most of the universe, as inflation proceeds, the field decays steadily toward its lower energy state and inflation ends. But in some regions, quantum fluctuations may push the field back up toward higher energy before it can decay. In those regions, inflation continues indefinitely, in fact, because the fluctuations keep happening randomly in a never-ending cascade. This idea is called eternal inflation, and it was developed by Andrei Linde and others in the 1980s. It proposes that the overall process of inflation never ends, not globally. In most regions, inflation ends and produces a universe like ours. But in other regions it continues, and from those regions new bubbles of ended inflation form, each becoming a universe in its own right, potentially with its own physical laws and constants, depending on the exact state of the quantum field when inflation ended. In this picture, our universe is one bubble in an enormous, perhaps infinite, collection of bubble universes. The Big Bang that began our universe was not the beginning of everything. It was a local event in a far vaster process that has been ongoing, that may have been ongoing forever, and that is still producing new universes constantly, in regions of the eternally inflating background that we cannot see and cannot reach. This ensemble of universes is what is meant by the multiverse. The multiverse is by its nature very difficult to test. If other universes exist beyond our own and are causally disconnected from it, separated by distances so vast that no signal can ever pass between them, then there is no obvious way to detect them directly. This places the multiverse idea in an unusual position. It arises naturally from mathematics that is well supported in other respects, but it cannot, at present, be confirmed empirically in the way that most scientific claims can be tested. There are some physicists who consider this a disqualifying problem, who argue that an idea which makes no testable predictions is not really science in any useful sense. There are others who argue that the multiverse is a legitimate scientific hypothesis, even if testing it requires approaches we have not yet developed. The debate is ongoing, thoughtful, and not yet resolved. What is worth noting is that the multiverse, if it exists, answers some otherwise puzzling questions. The physical constants of our universe, the strength of gravity, the mass of the electron, the cosmological constant that governs the expansion of space, seem to be finely tuned in ways that make the existence of stars, planets, and life possible. Change many of these constants by even small amounts, and the universe becomes sterile. In a multiverse, this might not require explanation. In an ensemble of universes with varying physical constants, we would naturally find ourselves in one compatible with our existence, because in all the others, we would not be there to look around. This reasoning, called the anthropic principle, is either deeply illuminating or deeply unsatisfying, depending on who you ask. It does not, after all, explain why the constants have the values they do. It merely argues that we should not be surprised they are compatible with life. Whether that constitutes an explanation is a philosophical question that has no consensus answer. Before we leave the deep questions and return to the quietly extraordinary story of what we do know, there is one more discovery that deserves careful attention, because it is both genuinely important and genuinely strange, and because it speaks directly to the long-term fate of the universe that began from nothing. In 1998, two independent teams of astronomers were studying a particular kind of exploding star, a Type 1a supernova, at great distances from Earth. These supernovae are used as standard candles in cosmology, because they have a known and reliable intrinsic brightness. By measuring how bright they appear from Earth and comparing that to how bright they should be, astronomers can calculate how far away they are. And by measuring the degree to which their light is redshifted, stretched toward longer wavelengths by the expansion of space, they can determine how fast those distant regions of the universe are receding from us. The expectation going into this research was that the expansion of the universe would be slowing down. Gravity, acting between all the matter and energy in the universe, should be pulling things together, providing a brake on the expansion that had been underway since the Big Bang. The question in 1998 was how strong that braking effect was. How much would gravity slow things down? What the two teams found was not a slowing expansion. It was an accelerating one. The most distant supernovae were dimmer than they should have been if the expansion were decelerating. And the only consistent explanation was that the expansion of the universe is speeding up. Space is not just expanding, it is expanding faster and faster. Something is pushing space apart at an increasing rate, counteracting gravity and driving the universe to expand ever more rapidly. This something has been named dark energy. The name communicates, with quiet honesty, exactly what we know about it. It is dark, in the sense of being invisible to our instruments, and it carries energy, in the sense of driving the expansion of space. Beyond that, its nature remains one of the deepest unsolved problems in all of science. The leading candidate for what dark energy might be is something called the cosmological constant, a term that actually appeared in Einstein's original equations of general relativity, though Einstein himself added it for a different reason and later called it his greatest mistake. It represents a kind of energy intrinsic to space itself, vacuum energy, the energy of empty space, even in the absence of any particles or radiation. In quantum mechanics, empty space is not truly empty. It is filled with quantum fluctuations, virtual particles continuously popping in and out of existence. These fluctuations carry energy. And that energy may be what is driving the accelerating expansion. Our best current estimates suggest that dark energy makes up approximately 68% of the total energy content of the universe. Dark matter, the invisible material we discussed briefly earlier, which does not interact with light but exerts a gravitational influence, makes up roughly 27%. And ordinary matter atoms, molecules. Everything you have ever touched or seen or been made of makes up roughly 5%. 5%. Everything you have ever experienced, every mountain, every ocean, every star visible in the night sky, every galaxy in every Hubble Space Telescope image, every living thing on this or any other planet, all of it together constitutes about 5% of what the universe actually contains. The remaining 95% is something we have named but not understood, quantities of matter and energy that pervade the cosmos but remain for now almost entirely mysterious. We live in the visible fringe of a much larger and mostly unknown universe. And that is not a discouraging thought. It is an invitation. It is the universe telling us, gently, that the story is not finished yet. And speaking of the story not being finished, it is worth spending a quiet moment on what the future of the universe might look like, given everything we know about where it has been. The universe began extraordinarily hot and dense. It has been expanding and cooling ever since. If dark energy continues to push space apart at an accelerating rate, and all our current observations suggest it will, then the long-term future of the universe is one of increasing emptiness and cold. In the near future, cosmically speaking, over the next few billion years, not much will change from a large-scale perspective. Stars will continue to form and burn. Galaxies will continue to evolve. Our sun will exhaust its hydrogen in about 5 billion years and expand into a red giant, ultimately shedding its outer layers and leaving behind a dim, cooling ember called a white dwarf. Long before that, the Earth will have become uninhabitable as the sun gradually brightens over the coming billions of years. The Andromeda Galaxy, currently about 5 million light-years away, is on a collision course with the Milky Way. In roughly 4 to 5 billion years, the two galaxies will begin to merge, a process that will take billions of years to complete, and will ultimately produce a large elliptical galaxy containing the stars and dark matter of both. Despite the word collision, the actual danger to individual stars is minimal. Stars are so small relative to the distances between them that in galactic mergers they almost never actually collide. They simply pass through each other's gravitational fields, swirling into new orbits in the merged galaxy. But over much longer timescales, the universe grows quieter. Over hundreds of billions of years, the rate of star formation slows as gas is used up. Stars that have burned out white dwarfs, neutron stars, black holes accumulate. Eventually, perhaps 100 trillion years from now, the last stars burn out, and the universe enters a long, cold, dark era, sometimes called the Stelliferous Era's end. After that, the universe will be a very different place from the one we inhabit. Cold, dark, populated by the remnants of dead stars. Slowly, over timescales almost impossibly long to contemplate, even these remnants will change. Black holes will eventually evaporate through a quantum process called Hawking radiation. Protons may or may not decay. Depending on the physics, this is an open question. If they do, all ordinary matter will eventually dissolve. What remains, in the end, will be in a sense we perhaps should not examine too closely before sleep close to nothing again. A cold, dark, sparse, slowly cooling universe approaching a state as close to emptiness as anything can approach. The universe may end, in the very deepest of futures, in a kind of thermal equilibrium called the heat death, not hot, but rather at the perfectly uniform, perfectly cold temperature of maximum entropy, where no gradients exist to drive any process at all. There is something oddly peaceful about this thought, if you approach it from the right direction. The universe began from nothing. And in the very far future, far beyond anything that can be meaningfully called the near term, it will approach something very close to nothing again. In between, for a brief cosmological moment, it made stars, and planets, and oceans, and life, and minds capable of appreciating the whole of it. We are in the middle of that story. And the middle, it turns out, is where all the interesting things happen. Let us slow down now and rest in what we have moved through tonight. We began at nothing, a concept so genuinely radical that even careful language struggles to hold it. No space, no time, no matter, no laws, nothing at all. And then, from that nothing, the universe. An expansion of space itself, carrying matter and energy outward in all directions. A fireball of quarks and photons and electrons cooling slowly, cooling over fractions of seconds and then over minutes, the first protons and neutrons forming. The first atomic nuclei assembling themselves in the first 3 minutes of cosmic time. Then, hundreds of thousands of years of a hot, opaque plasma. Light trapped inside it, bouncing endlessly off free electrons, unable to travel. And then recombination electrons settling into orbit around nuclei, the fog clearing, light escaping, the universe becoming transparent. And that ancient light is still traveling. It is all around us, even now, as a faint microwave glow, the oldest light in the universe. Then the Dark Ages. Hundreds of millions of years of quiet, of expanding gas clouds, of gravity working in silence. And then, in some dense corner of some gathering cloud, the first star lit up. The universe had made light of its own for the first time. Cosmic dawn. The first stars burned hard and died young and magnificent, and in dying they made all the heavy elements the universe had lacked since its beginning. Carbon, oxygen, iron, scattered across space in the violence of supernovae, enriching the gas clouds from which the next generation of stars and planets would form. Galaxies assembled. Grew, merged, the Milky Way took shape. A cloud collapsed into a solar system. The sun ignited, the earth formed, the oceans appeared, life began. Cells grew complex, animals emerged, and eventually, here we are. And then we stood at the boundary of the story, where the science gets quieter and more speculative, and we looked at the ideas that try to reach beyond it. Inflation, stretching the early universe by an incomprehensible factor in the first fraction of a second. Hawking and Hartle's no-boundary proposal, in which the universe has no edge in time, no moment of beginning that required an external cause. Vilenkin's quantum tunneling from nothing, in which the universe arose spontaneously as a consequence of quantum probability. The eternal inflation that may have spawned an infinite ensemble of universes, each with its own laws and constants. And then the mystery of dark energy, the invisible force that is pushing space apart at an accelerating rate. And dark matter, the unseen substance that outweighs all visible matter 5-1. And the quiet, humbling arithmetic that everything we can see and measure and have ever touched is about 5% of the whole. These are not the boundaries of failure. They are the boundaries of what we have managed so far to illuminate. And what we have illuminated is extraordinary. There is something worth holding gently as the night grows softer. The history of our understanding of the universe's origin is, in a way, a story about the willingness to follow evidence somewhere uncomfortable. For most of human history, the universe was assumed to be eternal, always existing, needing no beginning, needing no explanation for its existence. Even in the early 20th century, when Einstein first wrote down his equations of general relativity, and those equations pointed strongly toward an expanding universe with a beginning, he resisted the implication. He added a mathematical term to his equations, the cosmological constant specifically, to allow for a static, eternal universe that matched his intuition. Then, in 1929, the astronomer Edwin Hubble published observations showing that distant galaxies were moving away from us, and that the farther away they were, the faster they were receding. The universe was expanding, and if it was expanding now, then in the past it must have been smaller, and further in the past, smaller still, and at some point everything must have been compressed into an extraordinarily small, dense state. The evidence pointed toward a beginning, and science followed. The term Big Bang was interestingly coined by the astronomer Fred Hoyle, one of the theory's most prominent critics. He intended it as a slightly mocking shorthand, but it stuck, and the theory it names has since been confirmed by evidence so extensive and precise that no serious alternative currently competes with it. The cosmic microwave background, first predicted as a consequence of the Big Bang and then discovered in 1965 by Arno Penzias and Robert Wilson, who initially thought the persistent signal in their antenna might be caused by pigeon droppings, turned out to be exactly the ancient glow the theory predicted. The measured abundances of hydrogen, helium, and deuterium match Big Bang nucleosynthesis predictions with remarkable precision. The large-scale structure of the universe, the way galaxies are distributed in vast filaments and sheets and voids across space, matches what computer simulations predict, starting from the tiny variations in the cosmic microwave background. Science is not a collection of certainties. It is a process of narrowing uncertainty. And the Big Bang cosmology, for all its remaining mysteries, represents one of the most successful narrowings of uncertainty in the history of human knowledge. We do not know what came before. We do not know the full nature of dark matter or dark energy. We do not know exactly how inflation began, or whether it happened in precisely the way current models describe. We do not know whether the universe is the only one. These are real unknowns, and they are worth sitting with honestly rather than papering over. But what we do know is quietly, steadily remarkable. We know the universe began about 13.8 billion years ago. We know it has been expanding and cooling ever since. We know how the first atoms formed and when. We know when the first stars lit up and why. We know where the elements in your body came from. We know the temperature of the universe when it was 380,000 years old to within a fraction of a degree. This is knowledge that no generation before ours possessed. Knowledge assembled over decades by thousands of scientists, using instruments of extraordinary sensitivity, following evidence wherever it led, revising their understanding when new evidence demanded it. And the knowledge keeps growing. Even as these words were written, astronomers around the world were observing distant galaxies with instruments like the James Webb Space Telescope, the most sensitive infrared space observatory ever built, peering deeper into the early universe than any instrument before it. They are finding galaxies that are older, more massive, and more complex than the theoretical models predicted they should be at that stage of the universe's history. Which means the models will need to be refined. Which means our picture of cosmic history will become slightly more detailed, slightly more accurate, slightly more honest. This is how science works. Not through grand revolutions alone, but through continuous, patient refinement, each observation adding a little more light to a picture that is always, in principle, slightly more complete than it was before. We are not at the end of the story of understanding the universe. We are somewhere in the early chapters. And there is something deeply comfortable about that, if you let it be. That, in itself, is a small and quiet kind of miracle. And now, perhaps, one last thought, the most gently humbling of all. You are not outside this story, looking in. You are part of it. The carbon in every cell of your body was forged in the core of a star that exploded billions of years before our solar system existed. The oxygen you are breathing right now was produced by ancient photosynthetic organisms that lived in the early Earth's oceans more than 2 billion years ago. The hydrogen in the water in your cells is primordial hydrogen that formed in the first 3 minutes of cosmic time, when the universe was a fraction of its current age, and which has been hydrogen ever since. Drifting through gas clouds and solar nebulae and oceans and living organisms, and now resting, for a moment, in you. The calcium in your bones was made in a dying star. The iron in your blood was scattered across space in a supernova explosion and drifted for perhaps billions of years before finding its way into the cloud that became our solar system. The nitrogen in your DNA was forged in the cores of stars too massive and too brief to leave behind anything but enriched space. Every atom in your body has a history that stretches back billions of years. Most of them have passed through several stars. Some of them have been in other living creatures, in dinosaurs, in ancient sea creatures, in microbes that lived in environments that no longer exist anywhere on Earth. They have been rock and water and air and life over and over again across cosmic time. And for this moment, they are arranged in the particular and temporary pattern that is you. You are not a visitor to the universe, you are a part of it, assembled by its processes over billions of years, briefly aware of its own existence, briefly capable of wondering how it came to be. The atoms you are made of came from the Big Bang. The complexity you are made of came from everything that followed. You are, in a very literal and not at all metaphorical sense, the universe looking at itself. And that quiet curiosity that brought you to a video about the origin of everything, that settled you into a comfortable position and let the words wash in, is itself a cosmic phenomenon. Curiosity did not come from nowhere. It evolved over billions of years of biological history in creatures that benefited from asking questions and finding answers. It is a product of the same universe whose origin it contemplates. The wondering and the thing being wondered about are made of the same stuff, tracing back to the same source. There is no word for the feeling this produces exactly, but it is something like recognition. Like the universe, in this moment, gently recognizing itself. 14 billion years of cosmic history. All of it, every expansion and every contraction of temperature. Every particle that formed and every star that burned and every galaxy that assembled itself from drifting gas, all of it led, step by quiet step, through an unbroken chain of causes, to this moment. To you. Here in the dark, eyes growing heavier. The universe began from nothing, and it made you. And here, at the end of the story, that feels like enough. Thank you sincerely for spending this night with us at the Sleepy Space channel. If the journey from nothing to everything left you feeling more peaceful than you arrived, if the scale of it all is doing what it often does, which is to gently remind us how small and how temporary and how remarkably here we are, then it has done what we hoped it would. If you would like to return on another night for another journey into the hearts of black holes or the surfaces of distant planets or the long, slow death of stars, we will be here. A like or a subscription helps us continue making these long, unhurried journeys into the cosmos, and we are grateful for every one. But for now, there is nothing left to learn tonight. The universe will still be expanding in the morning. The ancient light of the cosmic microwave background will still be filling all of space. The stars will still be out there, quietly doing what they have always done, converting hydrogen into heavier elements, continuing the long story that began before any of them existed. And you are still made of all of it. Sleep well. Good night.